So here are my notes so far for Colloids Lecture 1. We went through what lyophilic and lyophobic colloids are. So lyophilic is solvent liking and lyophobic is solvent hating. And for something to be a colloid, the particle size has to be between 1 and 1000 nanometers. So if the particles were below this size, then it would be more of a solution and the particles wouldn't scatter light. Whereas if it was above this size of 1000 nanometers, then the particles would start to be affected by gravity and it would start to sediment. So one of the other reasons that we know something's a colloid is if it scatters light, which is the Tyndall effect, we can see light going through it. So something, for example, like fog would be a good example of a colloidal system. So it was lecture 1, we were going over lyophilic colloid examples. So we were going to look at micellar solutions, which are also known as association colloids because micellars come together and the surfactants associate with each other. Also polymers in a solution and vesicles. So vesicles are a bilayer of surfactants or lipids that are in a sphere and they can hold water in the middle or a drug in the middle, for example. And we had a little look at actually why micelles form, just as a reminder from our surfactant lectures the other week. So this is a surfactant here and it's in water, and the hydrophobic tails are very, very rigid in the water and it's forcing the water to cage around it, reducing the mobility of the water molecules. And then when we get the formation of micelles, obviously the hydrophobic tails are all coming together because they want to be together, and this means that they have more mobility and the H2O, the water, also has more mobility as it's with the hydrophilic heads. So actually it looks more ordered, but it's less ordered because here it's very rigid and ordered, here it's less ordered, so that's how we know that something is entropically driven. So we went on to looking at the CMC, which is the critical micellar concentration, and that's the point at which micelles start to form. So some of these factors are the length of the hydrophobic chain. So if you have a longer hydrophobic chain, then they're going to want to be away from the water even more if they're longer. So this will drive the form of micelles, and this will then decrease the CMC because the rate at which micelles form is going to be quicker. Another factor affecting CMC is the length of the hydrophilic head group, so these head groups here. If you increase the hydrophilic group, then the drive for micelles is less, because obviously this hydrophilic group doesn't mind floating about. It's going to overpower the fact that the little hydrophobic tails want to be together, so that's going to increase the CMC. So the time at which micelles form is going to be further on. You're going to need more of those type of surfactants with a long hydrophilic head to then start off the micelle formation. They're called diblock polymers, so they're usually non-ionic, so they'll have no charge, but we have a hydrophilic head point and a hydrophobic point, and you can make this hydrophilic point even longer. So then we also have the nature of that head group, so whether it's charged or if there's any counterions in the solution. So for ionic here, you can see that the heads have a positive charge, and that's going to repel one another. So when they've come into this micelle, these heads, like I just said, are going to repel each other, and so not as many are going to be able to fit together in a micelle. So as here, so there are not as many surfactants in the micellar structure. However, with non-ionic, which is what we saw here, so there's no charges at all, but this is a hydrophilic part and this is a hydrophobic part, it's going to lower the CMC. There's going to be greater aggregation. So aggregation is the surfactants coming together. No heads are going to be repelling each other here. So they're going to come together and aggregate more, and actually the micelles are going to be bigger too because they can come together more. This was an example, PEO, this head here. So just to summarise the factors affecting the CMC, if you increase the size of a hydrophilic head, then the CMC will increase, as the micelles are less likely to form. You'll need a higher concentration of surfactants to form micelles. So that's kind of explaining the size of the hydrophilic head. As well as these factors affecting CMC, there are external factors. So one factor is temperature. If you increase the temperature, you're increasing solubility, so the drive for micelles is lower, so you increase the CMC. So if something's more soluble, it's more likely to want to interact with the water. The drive to make micelles is lower, so then this increased critical micellar concentration. You're going to need more surfactant for the micelles to form. Adding electrolytes, so this is things like salt, for example, it's charged, it affects the ionic surfactants and decreases the CMC. So when we add an electrolyte, NaCl, if we add this, it reduces the impact of repulsion between the heads here, it comes in between. So the more molecules can then come in and enter the micelle, and this decreases the CMC because we can get more micelles. So it's easier for the micelles to form because the repulsion charges around here aren't as strong. Lastly, we have adding organic molecules. It can either increase or decrease CMC. It depends on how the organic molecule affects the hydrogen bonds within the water. So we've got 3 examples here. We can add alcohol, and that usually decreases the CMC. So alcohol will decrease repulsion between the surfactant heads, a lot like the electrolyte here, then decreasing the CMC. If we add sugar, we know that sugar is very soluble and it hydrogen bonds very well to water. So this drives the formation of micelles, and it's called a structure maker because water gets even more happy being hydrogen bonded. And when a surfactant comes in, it's like, well, what is this? Quick, make micelles. I don't want that hydrophobic thing in me. I'd rather have this sugar. So it decreases the CMC, so micelles are more likely to form more quickly. And lastly, we have urea. So that doesn't really interact with water. It's it kind of breaks up the water structure, and it increases the CMC. So by increasing the CMC, you're going to need more of the surfactant to make the micelles. So that is lecture 1 of colloids. I'm going to carry on and do lecture 2, and we'll carry on then.